Hey, how's it going, guys? So in this video, we'll look at quantized embeddings. So how you can use these quantized embeddings in your application to reduce the memory requirements as well as the storage requirements. So first, we'll look at why you need to quantize and how you can quantize the embeddings. And then we'll also check the benefits we get from quantizing your embeddings and also check the model performance in terms of accuracy. So let's start with why we want to quantize. Basically, quantization is a process of converting your floating point numbers into integers or even binary. So you are going from higher precision to lower precision. And this will naturally reduce the memory requirements. And here I have a screenshot from our Hugging Face blog, which shows how much storage and cost you would incur using floating point 32-bit embeddings. So here in the first row, we have a model that produces 384 dimension embedding. And if you wanted to store 100 million embeddings, it would take 143 gigabytes of storage. This is pretty huge, and we can use quantization techniques to reduce these kind of requirements. So before we dive into the process, let's first get to know the dataset. And basically, this is a dataset from Stack Overflow. And it has like 3 subsets in Hugging Face Hub. We will look at them individually just after this slide. First, let's load the dataset, and here I've loaded all of them and then converted to pandas. So I have the data frames for corpus, the queries, and the scores. So if we look at the queries has 2 columns, ID and the text. So the text is the query submitted by the user. And if we look at the corpus basically contains the title and the text of the answer, and also an identifier indicated by _ID. And then you have this scores, which actually maps from query ID to corpus ID, basically saying for this query, this corpus is relevant. And you can, for the same query, you can also have multiple corpus or multiple answers that are relevant. So for this 16708, we have 2 rows here. So multiple answers can be relevant for a given query. So now that we know the dataset, let's go ahead and embed the corpus first, because this corpus is the sort of a knowledge base for us. And in order to do that, we will first use the mini LM model from sentence transformer, and then we will combine both the title and the text and then extract the embeddings. By default, we'll get floating point 32-bit embeddings. And in sentence transformers library, you have this function called Quantized Embeddings, and you can specify what level of precision you want. So here I've specified ubinary for binary embeddings and uint8 for 8-bit integer embeddings. Now if we look at the memory uses, for 32,000 text that are in the corpus, the standard embeddings will take about 47 megabytes. If we look at the 8-bit integers, it only takes 11.78 megabytes. And the binary embeddings, it only takes 1.47 megabytes. So this is quite a lot of reduction in terms of memory usage. Similarly, when you store it in the disk, the storage will also decrease as you go down the precision. So let's create the nearest neighbors index, because we want to source our corpus using the queries, right? In order to do that, I have chosen Quantize as the library to do this. And almost all of the index in Quantize, they need the dimension of the embeddings. So we extract that one and then create a binary index. In Quantize, you can use index binary flat to create a binary index. Similarly, we create a floating point 32 index using index flat. And then for 8-bit integer index, you have to use index HNSWSQ, means scalar quantized. And you also need to specify a couple of extra parameters saying what is the bit size. And the 16 here is a hyperparameter for this index, which is not relevant. And you also, for this particular index, you have to train And I've passed the same embeddings that I will also add to the index. And now that we have our indexes ready, let's define a helper function which will query the index and then return the relevant answers from the corpus as a data frame. So in FICE, every index has a function called search where you can pass two-dimensional array, and then k is the number of items you want it to return, and then we loop through them together and create data frame out of it, and then append to the data frames output list which I return. And just to test, I'm passing the embeddings of the first item in the corpus as the query vector. And because of this, I also expect the first item in the corpus to be the first result, right? Because the embeddings are same, so hence it should be the first match. So let's look at it. And sure enough, the first item in the corpus is the first result here with the distance of 0, and this corpus has a distance of 72 and 94 and so on. So this is the output that we get from this search answers function. Now let's create query embeddings. So again, same approach as before. We take the text from the queries data frame and then use the model.encode to find the standard embeddings and then quantize the embeddings into 8-bit integer and binary embeddings. And then we call our search answers function using these embeddings. Now let's try to evaluate the model performance. So we have results from all three indexes, right? And if we want to find out how good the embeddings are and how good the results are, we need some kind of metric. For this purpose, I've chosen recall. So usually in information retrieval tasks, recall is one of the most common metric that you would use. And the formula is also very simple. So you take all of the relevant items that you retrieved divided by all of the relevant items that you should have retrieved. So in order to do that, I have created a list called expected results, which basically stores for every query what are the corpus IDs that are relevant. So for the first query, we have only one corpus that is relevant. So this is the ID of the corpus. And for the second query, these three corpus IDs are relevant. So we will use this later on to evaluate the model. And here's a function that I've defined called compute recall, which will take the expected results that we previously computed and the results from different embeddings. So basically here we loop through them together and then find out how many relevant items did we retrieve, and then compute the recall, and then finally we calculate the average of all the recalls and then return it. And using this function, we compute the recall score for all of these kind of embeddings. If we look at the results, the floating point 32-bit embeddings has the highest recall score. So the recall score ranges between 0 and 1, where higher value means better results. And as we go down the precision, here the 8-bit integer has a score of 0.5 and the binary has 0.46. Even though the recall scores are going down, the advantages that we have in terms of reduced disk space and the memory requirements, this might be a very attractive solution to use the binary or 8-bit integer embeddings. But this does not mean that we have to use these embeddings on its own. So we can combine multiple kinds of embeddings to give faster results, but also accurate results. So let's take a look at how we can combine both of these together. So basically the idea is first you compute the standard embeddings and then you binary quantize your query embeddings and then search on the binary index, which let's say gives you the candidates C1, C2 up to C10. And then what you do is load the 8-bit integer embeddings from the disk for these 10 candidates only. So at a given moment, you only load 10 8-bit integer embeddings in the memory. And then you compute the dot product between the 32-bit query embeddings against the 8-bit candidate embeddings. And then finally, you sort the candidates based on this dot product. And then you will see the performance improvement as well. So combining the quick execution of the binary index and the accurate dot product between the 8-bit integer and 32-bit query embeddings will give you the best of the both worlds. So this is all I wanted to share for today. I hope you found it useful, and see you next time.